Okay, in today's lesson, we're going to look at how to solve quadratic equations by complete the square method. Completing the square method. That's what CTS stands for. And we're going to do some problems a little bit later on in the worksheet. So the first thing I'm going to do is I want to talk about this. And completing the square, in my opinion, the process that the state or the general process that most mathematicians and textbooks show is really very cumbersome and it's not really very useful if there's another way of doing it. Completing the square technique is basically what I've already showed you is changing a quadratic equation and putting it into vertex form. That's the process they call completing the square. And then they have this big elaborate process that they go through for completing the square, which I've already showed you a much easier method for doing so back in an earlier section. And I'll reference that and show you that again a little bit later. But I am going to show you this method because there are questions that pop up in state tests and things that you're going to go through later. And they ask you questions about this process. So I'm going to show you how it works and what's going on. What do they mean by completing the square? Okay. Well, just like perfect square numbers, there are perfect square trinomials. These are the three terms, ax squared plus bx plus c. That's a trinomial. Perfect square trinomials. And they're called perfect squares because they can be represented by the area of a square. So I have a square. Both sides of a square are equal in length. The area of a square is s squared. Hence all these names. That's perfect squares, things like that. This is why it's called that. Okay, so we're looking for things that are going to be perfect squares. That's a number squared. Some examples of perfect square numbers that you are familiar with: 1, 4, 9, 16, 25, 36. And those are perfect square numbers because they come from numbers being squared. Okay, so that's the concept we're going to be following. And when we talk about completing the square, we're looking at a way to make something a squared number. That's what we're trying to do. So what are perfect square trinomials? Perfect square trinomials, they do the same thing. A trinomial of this form, ax squared plus bx plus c, can be factored into a square of a binomial. In other words, this right here can factor into something that looks like this, where it's the same factor twice. So then I can write it as a square of a binomial. A two terms is a binomial. This is a binomial squared, or the square of a binomial. That's the process we're using for completing the square for quadratics. We're going to take something that looks like that and write it as something squared, maybe plus or minus something on the end. Okay, so this also represents the area of a square. Okay, so if I have a square, the area of the square is this polynomial right here, and the side lengths are x plus p, and that's what we end up getting there. Okay, so this concept is here. This is how we are going to work and complete this square process and this understanding. All right, so the concept of completing the square is to take any trinomial that is not a perfect square trinomial and modify it so that it becomes one. Okay, not all trinomials are perfect squares. So we're going to take the ones that aren't perfect squares and modify them in a way so that we get something that is a square of a binomial in it. Okay, so here's the process we're going to follow, and I'll walk you through this whole thing. I'll let you see it all. So you can like copy it down if you wish to do so. It's not very difficult. It's a lot of words, but it's very simple what's happening. So if you remember our factoring technique for 4 terms, all right, so here's my square. I'm going to break it up into 4 other squares. Okay, and so what goes in here? So if I start with this simple form right here, this is not a perfect square. It's not even a trinomial. We're going to make it a trinomial. Okay, and to complete this square. So what's happening here is the first term goes in this box right here. Okay, and then the middle term, this number right here, this b number, what we do is we cut it in half, and we put half of it on each of the diagonal boxes, like that. So whatever that number is, if it was a 6, we cut it in half, then this would be a 3x and a 3x right here. If it was a 5, then we cut that in half, and it'd be a 5/2 and a 5/2 here. That's what's going on there. Okay? Divide the x term coefficient in half, put each half in the second and third box, like so. To complete the square, the fourth box, you need, because this right here, when we do GCF, this right here, if I have that, that's an x. That times that is that. That times that is that. That times that has to be that. So that's the only things that can happen there. So then this box is that number squared. Okay? It will always be whatever half that number is squared. That's the last box you need to complete it. So because the original problem did not have any third term, but I need that third term to complete the square, I will add that number to complete the square. But because I can't change the value of this actual problem, I also need to subtract the same value. So I'm adding and then subtracting the exact same number. The first 3 terms are a perfect square trinomial. So I can write them as something squared, which is that right there. This half number, this b/2, is the number that goes right here. So it'd be x plus that, and then that quantity is squared. And then since I had to subtract the same value, that just gets tacked on to the end. And you will notice that this looks exactly like the vertex form of a quadratic. Okay, so keep that in mind for later reference. But there it is. This is how the process of completing the square. This is what's going to happen. Now, as we move along, this becomes a little bit more difficult because this polynomial up here that we're going to be using is going to be different and it gets more complicated. So let's look at the next form. It's a little bit more advanced. This time, I actually have a number here, okay, a third term, okay? And so we're going to do the exact same process, but what we have is we want to get this number, which is already here. We're going to move this out of our way, okay? We're just going to slide it out here because then I can look at the problem just like that, which is exactly the same as the simple term we had on the other side. And to complete the square with this piece right here, I simply do exactly the same thing we did on the other side, which is take the middle term, cut it in half, and square it, and add that square, and then subtract the same thing. See, the plus c just got moved out. These first 3 terms that you just created right there, that part right there, that is the perfect square trinomial. And then everything after that, all of this, just gets combined together into a single number. I just changed the order so that I don't have any sign conflicts. But see, minus b/2 squared plus c, so c minus b/2 squared, same thing, just changed the order. And this right here is just simply a number. This will just become another number. Okay, again, being in vertex form. So I know there's letters here and stuff, but that's what's happening. Okay, so if there's a number on the end, just move it out of the way. Complete the square with the first part. Okay, and then when you subtract that b squared, that b/2 squared, just combine it with the number that was already there, and you will have completed the square. Now, the next advanced form. Notice this time, there's a number in front of x squared. Okay? So how do I complete the square here? This is why this is very challenging. Okay? Because you have to deal with it. Now, they're going to show you this process where you're solving an equation. Okay? And that's fine. Solving an equation using completing the square is a little bit different than changing a quadratic to that form by completing the square, because you can get rid of the a very easily. and make it into something that looks like that. There will be fractions involved, just so you know. But if I keep this process here, then this is what's happening. Again, I have to have an x squared, not with an a in front. So I have to actually factor out an a from each term. So remember, factoring an a out just means I'm going to divide every term by a. So if I take out an a from each term, this is the result I get when I factor out an a. And I'm going to complete the square with that process right there, with that thing. And you'll see that that looks very similar to this form right here. Just uglier fractions. So what do? This is the constant. So move that out of the way. Take those terms right there. Take the middle one, b over a, divide it by 2, and square it. And you get that right there. So I'm going to add that term, and then immediately subtract that same term, and then don't forget the last thing that we moved out. So those three things become that. And these two terms over here just combine together and add together, give me a simple number. When I get this number here worked out, the last step I have to do is I have to redistribute this a back through. So I'll take a times this quantity, and then a times whatever that number is right there. And again, it'll just be a number. So if you look closely at it, I know there's a lot of letters in here, but this is basically the vertex form. So we can go through this whole entire process like they're talking about, but that's the process they want you to understand, is that you're taking the middle term, the b term, this number, the coefficient in front of x, you're taking that, you cut it in half, and you square it, and then that added to these two terms becomes a perfect square, and then you subtract the same number and combine it with the constant that was already there, and that gives you your remaining constant over here. This is how they do this. Okay? Here's my method. This is vertex form. Okay? It's just easier to do this, and it works no matter what format I have. Find the vertex. The A is your leading coefficient. Once you have the vertex, put it into this form, and you have the completed square format. This is exactly what they want you to do. This is the end result. So my end result is exactly the same as that end result right there. So whether I'm changing a quadratic function, so it's in vertex form, or if I'm solving a quadratic equation in vertex form, this process is exactly, the end result is exactly the same. Just the method for getting there is slightly different. Okay? I think my method is a little bit easier, but you'll have to be the judge of that one. I will show you how this works side by side and see, so you can see the difference. I'm going to go grab a problem over here, and I'll show you the process that they have. Let's see. Well, this one's pretty simple. So here's this one. I'm going to do y equals 2x squared plus 12x plus 2. Okay? And we're going to use their method. And then I'm going to show you the same process using my method. I would prefer that you use my method, but you need to understand their method too. You can use either method you want. It's really fine with me. So to complete the square using their method, I have to first get rid of the 2 by factoring the 2 out. So y then becomes 2x squared plus 6x plus 1. So that's what I have there. Then I have to take this, and now I'm going on the inside only. There's the x squared, there's the 6x, and then I have to take this number and divide it by 2, and then square it. So 6 divided by 2 is 3, and I have to square it. And then I immediately subtract the same thing, and then there's the plus 1 that I moved out of the way. So I can stick these two things in there. See, so I'm adding 9 and subtracting 9 at the exact same moment. These three terms right here become the perfect square trinomial, and that becomes x plus 3 squared. All three of these terms become this. Okay, basically what we did is we factored that out and got that. And then over here, this is minus 9 plus 1. So a negative 9 plus 1 is a negative 8. The next step is to distribute this 2 back through. And so you get y equals 2x plus 3 squared minus 16. So there is their process. That is how they do it. And it's all fine and dandy when they're nice integer numbers. Okay, but you can get some ugly fractions in here, and you'll see that you'll get fractions also. No matter which method you use, you're not going to avoid fractions. So here is my method. So my method requires me to find the vertex, so that means I'm going to use negative b over 2a. Okay, and then in that process, I get a negative, b is 12, and a is 2. And so this right here is going to be 12 divided by 4, which is negative 3. I'm going to take negative 3, and I'm going to plug it back in and find the y value that goes with it. So plugging this in here, this is going to give me 9, 18. This right here is minus 36 plus 2. So this is 20 minus 36, or negative 16. So this here is the h, this is the k, and that is a. So my answer is y equals a, x minus h, so x minus a negative 3 squared, and then plus k. K is a negative 16 minus 16, and there you go. I get the exact same answer that they have. I just find the vertex, which would in graphing aspects of things you're going to find anyway. I don't have to go through this process to remember this process. I just simply find the vertex and then plug it into vertex form. It's that simple as long as I remember vertex form. Okay, but you need to understand the method that they're doing. This is the complete the square process. Okay, and this over here is my method. So this is Miller's method, and this is the government method. Okay, and you can do either one of those two methods right there. But the process is the same. So I can use this now. Now, when do I need to change polynomials or quadratics into this format? The actual changing it into vertex form, other than the fact that I'll ask you to do that as a question. Mathematically, when is it ever done? It's really done in a couple of local areas. There's a section called conic sections that you do in Algebra 2 that requires you to change things into vertex form. And you have to use this process, but you can still use my method. Okay, you can complete the square, or you can use my method. It works the same in both cases. And there's also a part up in calculus where you would have to change it into this format right here, okay, in the vertex form, and use it to continue a problem. And again, even in that scenario, you can use either one of the two methods. So there's really, whichever one you like the most, that's the one I would work with. What you're going to do is you're going to then turn around and solve these things. So the actual problem that I took this from, and you can see it over here, okay, and this problem right here is walking you through. Solve this quadratic equation by the factoring method. Okay, so by factoring method, I'm going to go through and factor this out. Let's go ahead and do this process here so you can see how this all works. And that's how everything's connected. So by factoring first, I have to take out the 2 because it's a common factor. I get x squared plus 6x plus 1 equals 0. And then I have a dilemma now. Okay? The dilemma is I can't factor this. There are no factors of 1 that are going to add and give me a 6. That's just not going to happen. So this is not factorable. Okay? So it said then let's graph this thing. All right? Identify all the major points and all that kind of stuff. So if I graph this equation over here, so if I graph y equals this, remember the solutions are x-intercepts. So I come over here and I graph this thing. Now we already have started the process. using my technique, we already know the vertex. I'm not going to do it again. So the vertex we know is at -3 and -16. This gives me my center value, so I can just go plug in some numbers over here. 2 above it, and they wanted the y-intercept, so we'll put 0 in here, and 2 below. Okay, so we need to work these out. We'll do this quickly as we can. If I plug in 0 up here, okay, if I plug in 0 in here, I'm going to get a 2, so I know that's a 2. Okay, and if I plug in -2, if I plug in -2, I'll get 2. -2 squared plus 12 times -2 plus 2. And what do we end up getting here? This is going to be 4. This is 8 minus 24 plus 2. So I get -14. -14. So this will be -14. And then -1 and 12, -1 plus 2. And this is going to be 2 minus 12 plus 2. And it looks like -8 and -8. Okay, so we can take this now, we can kind of graph this out. So here's -1, 2, -3, -4, -5. And we got to go down to -16, so let's divide by 2's. 8, 10, 12, 14, 16, 18, and 2, and 4, and 1, and 2. So 0, we have a 2. -1 is -8. -2 is -14. -3 is -16. This is at 14. And this over here is at 8. And so I can see clearly that at -6, I'm up at 2 again. Because it has to be symmetric. So I can draw this graph. And what I notice here in looking at this is, hey, this graph crosses the x-axis, so it has solutions. But look where they're at. They're in between here, so they're like some other kind of number. So our question then becomes is, well, I can't factor to get those, so I have to find another method for getting those. And this is what this technique for completing the square is used for, is being able to find those things. So let's go ahead and take a look at it. If you look out here at this next question, okay, so again, things to understand here. Since the graph crosses the x-axis, it has 2 solutions. But I can't find the solutions by factoring, so I need another technique. And this is one of the techniques that's completing the square. If I put this into vertex form, then I can solve this equation and find those 2 solutions. And that's what they're looking for in this lesson. So what is this in vertex form? Well, we already found it. We found it over here. Okay. It's that right there. So I'm going to rewrite that over here. So it's y equals 2x plus 3 squared minus 16. So I have that right there. Now, to find the x-intercepts, I have to take that and make it equal to 0. So when is this minus 16 equal to 0? So we're going to solve this. To help you solve this, I want you to see this quantity right here as a single object that I need to get by itself. So I'm going to use algebra techniques, which means I'm going to add 16. So I get 2x plus 3 squared equals 16. So you add a 16 to both sides, I get that. Then we're going to divide both sides by 2. And so now I have x plus 3 squared equals 8. So how do I undo a square? What process do I follow to get rid of a squared number? Well, that's where I do the square root. I'm going to take the square root of both sides. And so that gives me my special note. When you take the square root of both sides, you must put a plus or minus the square root. On one side. So that means I'm going to undo this square. So that means this side's going to have a square root. So I'm going to square root this side, and this is going to cancel out. And then this side will still have a square root with it, so that's the one that gets plus or minus. So this becomes plus or minus the square root. So this is x plus 3 because the square root squared undo each other. It's like adding one, then subtracting one. They undo each other. And this side becomes plus or minus the square root of 8. You have to have the plus or minus in here because when I square a number, 2 squared is 4. Negative 2 quantity squared is also 4. So there's 2 possible answers. That's the plus or the minus answer. I still want to find what x is, so I need to subtract 3 from both sides. This does not combine with a number. Only square root can go with its square root in some fashion. It's very, very, very tricky here. So you can't combine anything to this right here. So then x would be written like this: negative 3 plus or minus the square root of 8. We put the number in front, the root on the end. So these are 2 answers. We also need to simplify a square root. Now we've already done the square root simplification. I will remind you about this. What we're looking for here is we're looking for that perfect square that goes into 8. 4 times 2. So this becomes the square root of 4 times the square root of 2. The square root of 4 is a 2. This just stays. This is the simplified form of the square root of 8. This is the form you need to use. So this plus or minus means I have 2 different answers. I have x equals a negative 3 plus 2 times the square root of 2. Or x equals negative 3 minus 2 times the square root of 2. Just like when we had those other ones, and factoring, we had x equals this number or x equals the other number. This is a single number. This is a single number. These are my 2 answers. And we can use the calculator to approximate these decimals. So let me show you what they are real quickly. So a negative 3 plus, and I'm just going to use the square root of 8 because it's easier to type in, the square root of 8. And I'm going to give it as a decimal. So this one right here is approximately, one second. Yes. Is approximately a negative 0.172. And then we'll do the next one. So a negative 3 minus the square root of 8. And this one is approximately a negative 5.828. So I want you to take those 2 looks right here, these 2 numbers, see this one, and look at my graph. Now look at that. A negative roughly 0.2, that's about a point, negative 0.2. A negative 5.8, that's about a negative 5.8. So these are the decimal versions. These are the actual answers here. Actual answers, approximate answers of those 2 x-intercepts. So that's how that works. This is the process you're going to be following. Okay? Whether you use the actual completing the square technique or you can use putting it into vertex form like I showed you, this is the process you want to follow for solving an equation of this type. Okay? And so that's what we're going to be doing. We'll do more of these together in class. But for now, that's the end of this video.